It's time for you to take on the last case study, which is going to look at Bitcoin's Lightning Network. As we visualize this graph and pull some information from it, you're going to be using a few of the techniques that you've learned throughout the course, finishing with the shortest path functions that you just learned. Let's take a look. The Lightning Network allows users to send Bitcoin to someone else using a peer-to-peer payment routing system settled in Bitcoin. It can be helpful to visualize it using a graph. What do you need to know about the Lightning Network? Well, each node in the graph represents a user. Some users have direct payment channels open between them. However, most pairs of users don't. To send payments, each channel charges a small routing fee to anonymously and securely pass on the paid amount towards the receiving node. To maintain privacy across the network, no intermediate nodes can know where the payment is going. And what this means is that the sending user node must calculate the cheapest route to the receiving user node before any payments are sent. In reality, the shortest path is calculated based on not only fees, but might also consider delivery time, reliability of nodes, and channel capacity. But for this case study, we're going to focus on fees. Before I let you loose on the task and the questions, let's take a look at what this is going to look like in Neo4j. So we can see lots of different user nodes that have channels going between them. You can see some users that are actually disconnected from the network, so they have no payment channel open. We can see one example here of an inactive channel between two users. User nodes have certain properties, including their status, as do channels. And notice that the status of a channel in this case is marked using its label. Finally, these two nodes are highlighted because you will be using them later on in the questions. So let's take a look. Create a new graph using the Lightning cipher. Save it in your favorites and answer the following questions. Which node is the most connected in the network? If you exclude inactive channels, does the answer change? What is the lowest active channel fee percentage in the network? What is the median active channel capacity? You'll need to use the percentile continuous function, and I've included the documentation in the student files. What proportion of nodes do not have any connection to any other node? These are the disconnected ones we saw in the diagram. Then the first of the more difficult questions. Find the top 5 nodes by active connections. Do any of their connections have connections to each other? Question 6. Callahan 5 lives in Spain and often sends money overseas to his brother, Corey493. These are the user aliases. Corey lives in El Salvador. So Callahan 5 can either pay a 2.3% fee with his bank or is considering using the Lightning Network. Callahan 5 and Corey493 do have an inactive channel between them, but they can't use it. Your task is to find the shortest node path and calculate the total fee percent that Callahan needs to pay. With that, you can decide if Callahan 5 should use the Lightning Network to send his money. Finally, Hendrix886 used to send money to Carson574 via a 3-channel path. That route is no longer available. Your task is to find out why. As I've said in previous questions, don't worry if you don't get all of these first time. The concept of graph is very different to anything you've probably covered in BI or data science before, so have a go at these before working through the answers that I provided, and good luck. Let's take a look at the questions for the Bitcoin Lightning Network case study. So the first thing I did was to make sure that I deleted the previous graph using that saved query. I then imported my Lightning Network cipher and saved that as a favorite. I ran that and it created the 375 nodes and 406 relationships. Now before we answer the questions, let's take a quick look at the database itself. So let's click the 375, and in fact I'm going to return all of the nodes so we can see the full thing. So here's our example Lightning network. We can see some disconnected nodes over here that have no channels to any other nodes. We can see different relationship types, inactive channels, and channels. And we can see some nodes down here that have multiple inactive channels. And so obviously it's always helpful to have a play around with this visually before you start to answer the questions. And the first question was, which node is the most connected in the network? So for this, I'm just matching user nodes that have a connection to any other node. For each one, I'm returning the alias and the count of associated nodes with the name channels. That gives me Salvatore72 as the most connected node with 7 channels. But then the question said, if you exclude inactive channels, does the answer change? So looking at my database information, I can see that there are only 2 types of channel. So all I'm going to do is force this relationship type to be channel, as opposed to inactive channel. Let's see if this changes the answer. And no, we still have Salvatore72 as the top ranked node. The second question was, what is the lowest active channel fee percentage in the network? So for this, I just want to return a list of channels that have associated nodes at both ends. I want to return a distinct list of channel IDs and the percentage associated with each one. I order the results by that fee percentage, ascending, which gives me 0.00005864%. The third question was, what is the median active channel capacity? So looking at the network briefly, we can see that capacity is one of the properties of the channel. So again, we're going to start by finding all the relationships that are active, so marked channel, that have nodes on either end. And since that's going to give us many values, I want to find the median of those values. So here I've used the 50th percentile. So the answer there is just shy of 3 million. It's probably worth me saying that the units here are not Bitcoin, but Satoshis, which are the units which make up Bitcoin. Otherwise, that would be a lot of money. Question 4. What proportion of nodes do not have a connection to any other node? So for this, we first match all nodes in the graph. And the way I've done this is within the where statement, I've referred to those nodes again, and I've said where those nodes do not have a relationship to any other node, and then simply count the number that we have left. So the answer there is 43. Question 5 was a bit more difficult, and we're going to do this one in 2 steps. So find the top 5 nodes by active connections. Do any of their connections have connections to each other? Okay, so step 1 is simply to find the top 5 nodes by active connections. For that, we use a match statement, making sure that we use the channel label for the relationship so that we exclude inactive channels. As we did before, we returned the nodes and the count of related nodes. We order that in descending order and limit the results to 5, which should give us Salvatore72 that we found earlier and 4 other users. Let's make sure that alias appears there on the nodes. So we have Salvatore72 here. So then the question said, do any of their connections have connections to each other? So what we want to see is all of the connections of these nodes. So modifying this query, instead of returning n and count m, we're just going to use them as inputs to the remainder of our query. So we change return to with, and we can still order those results and limit to the top 5, which still gives us our top 5 nodes. But then what we can do is create a new match statement to find nodes with the alias n, which is what we've passed down from the other query, that have a connection to any other node, which we'll call p. And so finally, we want to return n, which are the top 5 nodes, and p, which are all their connections. and we can see that some of their connections are, in fact, connected to each other. Question 6, and I think this was probably the most challenging of them. So this is reusing the shortest path syntax that we learnt in the last chapter. So we're trying to find the shortest connection between Callahan 5 and Corey 493. I've created that path and used the shortest path function to link a chain of active channels only between the start and end nodes. And to start with, I'll just return the path. So that's interesting. We can see the inactive channel there that they presumably used to use, just over here. And then we can see all of the other channels which they're now having to route their payment by. So to get the total fees, we need to unwind this path into its individual component relationships. And so instead of returning path, let's use the unwind function to unwind relationships in the path as R. And then for each of those, we want to return the channel ID, so r.channel ID and r.fee%. That returns us 8 channel IDs with a percentage for each one. We can count them visually in this diagram, and we can see there are, in fact, 8. If we follow the channel IDs around, we can see the first one ends in 3K3, which is going from Callahan round to Corey. This one ends in 3K3. We've got the right channel. So that gives us all our individual fee percentages, and so all we need to do now is to create a sum of all of those to find out the total fee. And so what we see is that the fee that Callahan needs to pay to send this money via the Bitcoin Lightning Network is tiny. It's 0.0022%, which is a fraction of what it's going to cost him to send it using his bank. And so considering fees only, in this case, he's going to choose the network. The final question in the Lightning Network case study was to find out why 2 users could no longer send each other payments. Although this question sounded difficult, with a little thought, it was actually possible to solve it with relatively little code. And the key was to use the specific information in the question. So we said that these 2 users, Carson and Hendricks, used to send money via a 3-channel path. So we know there are 2 nodes and 3 channels that separate them. I've given the 4 nodes in total the aliases A, B, C, and D, and I'm just going to return all of those to see what's going on. As expected, we see them separated by 3 channels, 2 of which are inactive, but both of those are coming from Emiliano. And if we hover on Emiliano, we see that his node status is inactive public node. So it looks like that is the reason why his 2 channels are inactive, and that's the reason why these 2 users can no longer send each other a routed payment via this path. Congratulations on reaching the end of this Graph Database Fundamentals course. I hope you enjoyed learning about this totally different approach to data modeling. We included a lot more exercises and challenges in this course, especially compared to others. So I'd love to hear from you in the feedback if you enjoyed those additions. Next, you'll shortly be presented with a short exam to test your knowledge on graph databases. Good luck, and see you in the next course.